Welcome to this video number 9 about active band rejection filter. A band rejection filter filters out one specific frequency. Very good. But all the other frequencies are passed without any problem. And here, let me get a laser pointer. We have the overview of such a band rejection filter, and at one specific frequency it's filtered out very good. Normally it's defined by the -3 dB, so the bandwidth, the normalized bandwidth of the filter normalized to this one specific frequency that we are interested in to get rid of. That could be the 50 Hz hum we have on all circuits due to the 50 Hz 230 volt AC wires we have in the housing today. That's just one example. The trick is to get the band rejection filter transfer function is that we use the first order low pass transfer function as we see it here, and here is the graph of it. And we replace S here by this new equation here, where we delta omega is the normalized bandwidth of the filter, and S is then replaced by S plus 1 over S to get this format here. Looking at this transfer function for the band rejection filter, we can see it's a second order now. And it has also as A0 and the delta omega in the equation. So suddenly we have here an upper equation. A0 is the band pass gain here in the low pass filter. We have here also. So both here and here we have that gain. We have something called the Q, the quality factor for the filter. This is defined by the mid frequency, actually the frequency we want to get rid of, and the bandwidth. And in our case here, the bandwidth is the delta between omega 2 and omega 1. So designing these kind of filters, we normally use Q and delta omega. So we replace it here in this transfer function with 1 over Q. So omega and Q is related to each other with the inverse. So now we have the band rejection transfer function as a function of A0, the gain in the passband, and then how narrow it is here. The Q decides on how selective it is. It's just the inverse of the band pass filter. So the higher Q we have, the more selective the filter is. And that's the same case here. The higher the Q we have, the more selective is it in removing one specific frequencies and the others are passed. Yeah, let's go further. We know a specific filter called the twin T filter. It's the band rejection filter. Here we can see a passive type. It is simply a combination of low pass and high pass filters summed together. And this passive twin T filter, normally it has a Q of 0.25, so it's not very selective, but we can actually increase the selectivity of this passive twin T filter by adding an amplifier into the circuit. And here we can see at this point here, we have it here, it's connected to the output of the filter, and the output here of the passive filter is connected to the input of the non-inverting amplifier. So then we have suddenly an active 20 filter, and we have the possibility to increase the selectivity of it, so the Q can become higher, and we can filter out a specific band of frequencies that to a higher degree, so they are attenuated more. The transfer function of this filter we can see here. Let's continue. When we compare the transfer function of the active T filter with our general equation of the band rejection filter, we can then compare the variables, and we can see in this case the K here is A0, so we also have A0 in here, and comparing here the factor in front of the S is actually the whole factor here. So we get from that the mid frequency, where we actually select the frequency we interested in getting rid of, can be found by this equation. The inner gain is coming from the op amp here. This is responsible for the inner gain. It's actually the gain factor of the non-inverting amplifier. The passband gain A0 is the inner gain from the op amp. And the rejection quality, the Q, is 1/2 and times the bracket 2 minus G. And the good thing about this setup, the active twin T filter, is that we can modify the quality factor of it by help of the inner gain without changing the frequency we want to get rid of. But there is a small consideration we have to take into account, and that is if G here becomes 2, we get a 0, and a 0 times 2 gives a 0, and then Q becomes very big, and a Q means it's actually moving some complex poles, and we can risk that the whole circuit here becomes unstable and even oscillate, but typically it can go to the one power supply rail, either the positive one or the negative one. So, and then it's locked up and don't work. So we have to watch out in our design that that the inner gain is less than 2. So how do we then design with these equations? Solving this mid-frequency, we solve for the resistor when we know the capacitor. So we would typically select the capacitor. We would also select the gain here in the passband. And we have to select our mid-frequency, the frequency we are interested in to get rid of. And then the Q is how selective should we be. So how many side frequencies are we interested to let pass? So finding R is done by solving for R on this equation. And then we can find by 2, either by A0 minus 1 times R, or we can find R2 based on a 1 value, and then 1 minus 1 over 2Q. Let's take a small example on how we actually design a 20 filter. We have here the mid frequency of 1 kilohertz, and we want a selectivity of the band rejection filter to have a Q of 2, and we pick the capacitor to be 1 nanofarad. So first we find the resistor value for the filter here on these places, and here we have to have a half resistor, so we should watch out for it not to become too small. So 2p, and then the mid frequency here, that was 1 kilohertz. We give this equation gives 159 kilo ohm, and the closest one we have in the E series is 158 kilo ohm. That's okay. Then we select R1, and it's sitting here, so this resistor should be in the kilo ohm range, between 1 kilo and 1 mega ohm, in order not to have a too big current flowing down here and loading our op amp. So depending on we are running on battery or have to be more considerate about the energy consumption in general, a 10 kilo ohm could be a good value, and we know it comes as a 1% resistor. So we use this in this equation to calculate R2, and it's 7.5 kilo ohm, and also can be found as a standard resistor value of 1%. So in principle we finished the design, but since we have the requirement of that G has to be smaller than 2, we have to check that and solve for G, and then calculate the inner gain of the amplifier that it's not too high. And solving that, we find out that the inner gain is 1.75, and that's below 2, so the design must be okay, and we can consider it stable, at least on our calculation wise. So now we can see the whole filter. I can see I have not given a value for 2 divided by 2, but we have to find 158 kilo ohm divided by 2 and place that in here. Yeah, so this is our active band rejection filter. The next step would be to simulate it, to see that we actually get the overall transfer function characteristic of it, and that it's filtered out the frequency here of 1 kilohertz sufficiently. Or do we need to do some tweaking of the filter or have a higher order? For the higher order, then we have to go in and look in a filter book and find another circuit that gives the option to go up higher. Or we could cascade another filter here that takes out a bit more, so do as even a filter, additional filtering of it. Yeah, let's take the next slide, and that's the end. Thank you for watching.